Hi everyone, this is K. Karthik from Institute of Aeronautical Engineering and Electrical and Electronics Engineering from Section A 23951A0206. Now I am going to explain about applications of Eulerian graphs in network security. Introduction to Eulerian graphs. One stroke graph. Eulerian graph theorem G can be traversed by single closed trial if and only if G is connected and all vertices of G are of even degree. The edges of a graph G can be drawn in single open stroke if and only if G is connected and precisely two of its vertices are of odd degree. Eulerian graphs are fascinating and important concepts in graph theory, with applications spanning network, security, circuit design, and more. These graphs characterized by the ability to traverse every edge exactly, once offer unique insights into the structure and connectivity of complex systems. Definition and properties of Eulerian graphs. An Eulerian graph is a mathematical concept in graph theory where every vertex or node in the graph has an even number of edges or connections connected to it. This unique property always allows for the creations of continuous path that traverses each edge exactly once, known as Eulerian circuit. Some key properties of Eulerian graphs include the fact that they must be connected and that the number of vertices with odd degree number of edges connected to a vertex must be 0 or 2. These characteristics enables efficient routine planning and optimization, making Eulerian graph highly valuable in network security applications. A graph is Eulerian if all vertices have an even degree. Semi-Eulerian traversable contains a semi-Eulerian trail, an open trail that includes all edges one time. A graph is semi-Eulerian if exactly two vertices have odd degree. Eulerian circuits and paths. Eulerian circuits, Eulerian paths. Applications in network security. Eulerian circuits. An Eulerian circuit is a closed path that traverses every edge in an graph exactly once, returning the starting vertex. These circuits are critically in network security, as they allow the efficient data transmission and route optimization without leaving any network segments unvisited. In graph theory, an Eulerian trail or Eulerian path in a trail is a finite graph that visits every edge exactly once, allowing for revisiting vertex. Similarly, an Eulerian circuit and Eulerian cycle is a Eulerian trail that starts and ends on the same vertex. Eulerian paths. Eulerian paths are similarly, but they do not necessarily return to the starting vertex. They traverse every edge exactly once, connecting two distinct vertices. Identifying Eulerian paths is useful for mapping network topologies and analyzing potential vulnerabilities in complex systems. Application in network security. Eulerian graphs and their associated circuits and paths provide a powerful mathematical framework for modeling and analyzing network structures. This allows network administrators to optimize routine, detect vulnerabilities, and ensure comprehensive monitoring and maintenance of their systems. Network security involves all controls, virus and antivirus softwares, application security, network analytics, types of network related securities, endpoint web, wireless, wire, firewalls, VPN, encryption, and more. Detecting Eulerian graph. Vertex degree. Analyze the degree of each vertex. Connected components. Identify connected components in graph. Cycle detection. Search of Eulerian cycles and paths. Detecting whether a graph is Eulerian involves examining the degree of each vertex and the connectivity of the graph. The first step to analyze the degree of each vertex. An Eulerian graph must have all vertices with even degree. Next, we identify the connected components of the graph, as an Eulerian graph must have a single connected component. Finally, we search for the presence of Eulerian cycles and paths by traversing the graph. If these conditions are met, the graph can be classified as Eulerian. A graph is Eulerian if all vertices have even degree, contains a semi-Eulerian trial, and open trial that includes all edges one time. A graph is semi-Eulerian if exactly two vertices have odd degree. Applications of Eulerian graphs in network security. Routine optimization. Eulerian graphs can be used to optimize network routing, ensuring efficient data flow and minimizing congestion by identifying Eulerian circuits. Network administrators can establish optimal paths for packet transmission, leading to improved throughput and reducing latency. Vulnerability analysis. Analysis the Eulerian properties of a network topology can help identify potential vulnerabilities. Detecting nodes or links that, if disrupted, would break the Eulerian nature of the graph, can reveal critical points in the network that require enhanced security measures. Network monitoring. Eulerian graphs can be used to develop efficient network monitoring strategies by tracking the transversal of Eulerian circuits. Network administrators can be identify anomalies, detect potential attacks, and ensure the overall health and resilience of the network infrastructure. The graph concerns relationship with lines and points, nodes. The Eulerian graph can be used to represent almost any problem involving discrete arrangements of objects where concern is not with the internal properties of these objects but with relationship among them. Routing optimization in network traffic. Eulerian graph play a crucial role in optimizing the routing of network traffic by leveraging the properties of Eulerian circuits and paths. Network administrators can be developed efficiently algorithms for packet routing, load balancing, and traffic management. Eulerian graphs ensure that all network nodes and links are transferred without repetition, leading to optimal utilization of network resources and minimizing delays. The ability to find Eulerian circuits within a network topology allows for the design of robust routing protocols that can adaptively reroute traffic in the event of link failures or network congestion. This resilience is essential for maintaining high availability and reliability in mission critical network infrastructures, such as those found in healthcare, finance, or national security domains. Routing optimization problems on network consist of finding paths between nodes of the networks in an efficient way. The performance of the network can be improved when routing optimization is used. Many solutions for the problems have proved to be useful for many real-world applications. Vulnerabilities analysis and attack detection. Network topology mapping analyze the structure and connectivity of network using Eulerian graphs can help identifying potential vulnerabilities such as bottlenecks, single points of failure, and unsecured entry points that could be exploited by attackers. Anomaly detection. Eulerian graphs can be used to model the expected flow of network traffic, allowing for detection of unusual or suspicious activity that may indicate a cyber attack. Deviations from the expected Eulerian patterns can serve as early warning signs. Attack path prediction. By understanding the Eulerian properties of network, security teams can be anticipate and simulate potential attack paths that can be intruded might take, enabling them to proactive address vulnerabilities and implement countermeasures. Efficient network monitoring and maintenance. Eulerian graphs play a crucial role in optimizing network monitoring and maintenance processes. By leveraging the properties of Eulerian circuits, network administrators can create efficient transversal paths to monitor all network nodes and links without redundancy. This allows for comprehensive yet streamlined network monitoring, reducing the time and resource required to maintain network health and security. Furthermore, Eulerian graphs analysis can help identify critical network bottlenecks, vulnerabilities, and potential failure points. By modeling the network topology as an Eulerian graph, administrators can proactively address issues and implement robust maintenance strategies to ensure the resilience and reliability of network infrastructure. With the aid of Eulerian graph algorithms, network monitoring and maintenance tasks become more efficient, enabling IT teams to quickly detect, diagnose, and resolve network related problems, ultimately enhance the overall performance and security of the network system. Resilience and fault tolerance in network topologies. Resilient network topology. Eulerian graphs can help design resilient network topologies that can withstand failure or attacks by identifying critical nodes and edges. Network engineers can reroute traffic and maintain connectivity even when parts of the network go down. Tolerance. Eulerian graphs enable efficient detection and isolation of network faults by analyzing the Eulerian properties of the network. Issues like congestion, bottlenecks, and single points of failure can be identified and addressed, improving overall fault tolerance of the system. Redundancy and backup paths. Eulerian graphs can help identify redundant paths in the network, allowing the seamless reroute of traffic when primary link fails. This builds the redundancy, increases and reliability and availability of the network, ensuring continuous service even in the face of disruption. Conclusion and future directions. As we have explored the fascinating applications of Eulerian graphs in network security, it's clear that this fundamental concept holds immense potential for further advancements. Moving forward, researchers and practitioners will continue to push the boundaries of the field, unlocking new opportunities to enhance the resilience, efficiency, and security complexity network systems. Conclusion and future directions.